On December 27, 2025, Mount Etna did something unique in 28 years. 5 days later, the volcano revealed something that deserves far more attention than it received. It's not about lava, it's not about ash, and it doesn't appear in a single civil protection plan for eastern Sicily. A road on the east slope of Mount Etna between the towns of GEOMAR and Riposto. The local authorities repaved it in the spring of 2025. By autumn, it had already ruptured again. A lengthy diagonal fissure caused the asphalt to buckle on both sides. The houses along the road have the same problem. Walls crack, door frames shift, and plaster breaks off cleanly, as if someone had scored it. The residents fill the cracks, repaint, and wait for the next one. This has been going on for decades, and it's getting worse. By the end of this video, you'll know why. No one in that area ever bothered to inquire. But first, you need to know what happened at Christmas. It started there. December 24th, 2025, Christmas Eve. Deep under Etna, the seismic network registered a change. Volcanic tremors increased. Hodin sensors indicated inflation. Something was pushing upwards. 3 days later, the northeast crater erupted. 2 paroxysms that day, with 500-meter lava fountains. The eruption columns shot up over 10 kilometers high. Boris Benke, volcanologist at INGV Catania, called it the Great Return of the Northeast Crater. This crater had been dormant since March 98. Its reawakening after almost 3 decades was Italy's headline. But what happened next really should have made headlines. The tremor subsided and the summit fell silent. Ash clouds from the Bocca Nuova diminished, then stopped. On New Year's Eve, Benke wrote that the volcanic tremor was even decreasing. All signs indicated that Mount Etna was falling asleep. But shortly after midnight, on the 1st of January 2026, the eastern flank split open. Not at the summit, not at 3,000 meters, where Etna usually vents. A fissure opened at the base of Monte Simone, an ancient crater from the 1811 eruption, at 2,100 meters above sea level. A study released in December 2024 had calculated that fissures at this specific altitude are 2 to 3 times less likely to occur compared to those near the summit. The magma definitely should not have emerged here. Lava flows poured eastward into the Valle del Bove, the vast horseshoe-shaped depression on Etna's eastern side. Within a day, the lava front descended to 1,400 meters. A 3.2-kilometer-long lava field glowed in the winter darkness, visible from the towns of Milo and Fornazzo. Every news channel showed the footage, snow and fire under the Sicilian starry sky. Spectacular, the INGV confirmed, no danger to inhabited areas. Behanke confirmed it, 5 kilometers from Fornazzo, flowing through an uninhabited valley. By mid-January, the eruption was declared to have ended, and every single report treated it as the entire story. No, it wasn't even close to that. The fissure didn't just happen to open up on the mountain. It opened on the eastern flank of Mount Etna, the same flank a German research team had been monitoring unnoticed from the seabed since 2016. What they found there turns this eruption from a spectacle into a warning sign. In 2016, the Poseidon sailed to Sicily's east coast. On board was a team from the GEOMAR Helmholtz Center for Ocean Research Kiel, led by marine geoscientist Morelia Urlaub. Her specialty: what happens when a volcano meets the ocean? It's a question hardly anyone asks. Off Etna's east coast, the team placed 5 acoustic transponders on the seabed, 1,200 meters deep. Each device pings the others once every 90 minutes. Even the most minute alterations in the sound's travel time allow the network to precisely pinpoint horizontal seabed movements, down to the centimeter. For a year, data and distances remained stable. Nothing stirred. In May 2017, the numbers soared. The research team checked the data. They ruled out tides, storms, and measurement errors. The pattern was clear. In just 8 days, the volcano's flank shifted 4 centimeters. No eruption, earthquake, or tremor. The movement was completely silent. It occurred 25 kilometers from the Etna crater, more than a kilometer deep on the seabed. If magma were pushing the flank sideways, the largest movement would have to occur near the summit, but the opposite was true. The largest displacement was at the very bottom, underwater, quite far from the magma, yet still on the volcano. Urlaub published her findings in 2018 in Science Advances. The conclusion was clear: magma is not pushing the southeastern flank of Etna outward. It is sliding under its own weight toward the Ionian Sea. Gravity. A wet book on a sloping table, it won't need to be pushed. It slides on its own because it's too heavy for the surface. Etna is over 3,400 meters high and rests on soft, water-saturated marine sediments. It's the same physics, but the book weighs billions of tons and the table slopes into the sea by an average of 14 millimeters a year and 3 to 5 centimeters at the surface. Too slow to ignore, too fast not to tear up every road on the eastern slope. Heidrun Kopp, a geophysicist and co-author of the GEOMAR study, stated quite simply, the entire slope is moving due to gravity. It is therefore quite possible that it could collapse catastrophically, which could trigger a tsunami throughout the entire Mediterranean Sea. A tsunami from the mountain where tourists ski in winter. That sentence truly sent a chill down my spine when I read Kopp's statement. Not because it's dramatic, but because it's carefully considered. A geophysicist from a leading European marine research institute chose the words "quite possible" for a Mediterranean tsunami. This isn't mere speculation. It's a scientist being deliberately cautious with a conclusion she really didn't want to make. Slides and eruptions aren't separate. They reinforce each other. It's no theory. In 2002, Etna erupted from its northeastern fissure. Earthquake swarms shook the eastern slope. Days later, the Pernicana fault ruptured, the northern boundary of the unstable flank. In Lingua Glossa, door frames warped. In Santa Venerina, walls split to their foundations. The fissure stretched for 18 kilometers, reaching all the way to the coast. The tourist station Piano Provenzana was destroyed. The eastern flank shifted by as much as 2 meters within just a few weeks. This was an eruption which clearly revealed the underlying mechanism. Ascending magma forced a vertical passage of molten rock up through the crust, giving the flank a significant lateral push. But the flank was already under pressure from gravity. So when it gave way, it tore the rock apart, creating new fissures. And these fissures offered new magma pathways. A self-perpetuating cycle. There's also a version that happens without any eruption at all. Researchers documented slow sliding movements on Etna's east slope. The flank lunges forward in sudden, powerful bursts, silently releasing an amount of energy equivalent to a magnitude 5.5 earthquake. No seismic signal, no rumbling whatsoever. The GPS stations only notice it after it's already happened. January 1st, 2026. A fissure opens at an altitude of 2,000 meters on the eastern slope in the Valle del Bove, just as the volcanic tremor subsides and all instruments indicate the eruption is dying down. The magma under pressure, it didn't remain at the summit. It forged a path deep within the unstable side of the volcano, the very part already succumbing to gravity's pull, where silent movements unleash earthquake-level energy, the same section that once shifted 2 meters from a single eruption a mere 24 years prior. The Valle del Bove, where this fissure opened, shows what happens when the process ends. This depression isn't just an ordinary valley. It's actually a colossal collapse scar, stretching over 5 kilometers wide and 10 kilometers long, opening out to the sea on its eastern side. About 8,000 years ago, the entire eastern flank of Etna broke away, sending 25 cubic kilometers of rock crashing into the Ionian Sea. To compare, that's enough to bury a city like Berlin under 40 meters of rubble. The collapsing mass raced down the slope, striking the water at a speed exceeding 300 kilometers per hour. Maria Teresa Pereschi from the Italian Institute for Geophysics and Volcanology reconstructed what happened. Her team tracked the debris for 20 kilometers across the seafloor. Then they found megaturbidite deposits, massive underwater mudslides triggered by the impact, that spread for hundreds of kilometers across the Ionian seabed to the Gulf of Sidra off Libya. Then came the tsunami. On the coast of Israel, over 1,600 kilometers from Sicily, archaeologists found Atlit Yam, a Neolithic village that was suddenly abandoned 8,000 years ago. Pereschi's team concluded that the wave reached these shores 1,600 kilometers away due to a flank collapse of the geological structure that Etna had freshly reopened on New Year's morning. I've delved into numerous volcanic hazard studies, but this particular one always draws me back. 8,000 years, and the flank slippage hasn't stopped since. The road between GR and Riposto, repaved by the municipality in spring, was cracked again by autumn. Riposto lies directly at the foot of Etna's flank. Just like Giare, just like Acireale, and even Catania's northeastern edge, where the Baroque churches of the old town are less than 30 kilometers from the unstable flank. 900,000 people live on the flanks and at the foot of this volcano. After her study was published, Urlaub described what the ground sliding looks like. Quote, "Currently," she said, "it's barely noticeable for residents. Roads are often repaved because of cracks. Houses need new coats of paint to cover up the fissures. Roads, paint, cracks. That's what 900,000 people see. What they don't see is the submarine flank, slowly shifting in silent 4-centimeter jumps. Above the waterline, Etna is one of the most monitored volcanoes on Earth. Over 100 GPS stations, summit and flank seismometers, tilt meters, satellite radar, crater rim infrared cameras. The INGV records every tremor, every inflation, every lava flow in real time. When the northeast crater erupted in December, the observatory had knowledge of it hours before the initial eruption. Below the waterline, where the flank would break off and plunge into the sea, where the catastrophic collapse begins, monitoring is far less extensive than above. No real-time data for the coast, no automatic alarm. Just the same handful of instruments that Urlaub's team installed in 2016, and something no monitoring network in the world has ever recorded: the transition from slow creep to catastrophic collapse. The last time this happened at Etna was 8,000 years ago. No instruments existed. No one knows precursors. No one knows if there would be hours, minutes, or no warning at all. An Etna flank collapse tsunami would absolutely reach the Sicilian coast within mere minutes. 2025 was the most active year at Etna in recent history. 3 distinct eruptive phases spanning from February to September, the northeast crater's reawakening in December, followed by the New Year's fissure, nestled deep within the eastern flank, at the very core of the slip zone. Over a 12-month period, more magma intruded into that unstable slope than in any of the preceding years and below it. Gravity doesn't just pause between eruptions. It won't wait for monitoring networks to expand or warning systems to be fully constructed. Urlaub specifically emphasized the absolute necessity for further fundamental research to better comprehend the intricate geological processes both on and around Mount Etna. The seabed network can be a great help. That was 2018. The network has 5 transponders. The threat has been published, peer-reviewed, and cited hundreds of times. The geological archives in seabed sediment. Evidence is cracks in roads and walls of every East Slope town. The New Year's Day fissure wasn't a catastrophe, it was a signal. And the most unsettling thing isn't what Etna did on January 1st. It's what the mountain is doing now, as the lava field cools and the cameras have moved on. The transponders on the seabed still ping every 90 minutes, measuring fractions of a centimeter, waiting for the next silent jump. Somewhere on the east slope, a wall is tearing slowly and cleanly, just as it always does. And someone will inevitably fill in that crack, paint right over it, and never even wonder what is truly tearing that wall apart. The only question is, will someone build a system telling 900,000 people when to stop and leave?